welcome back to our computing lessons. We've completed Basic 7 and Basic 8, and then we now want to discuss the Basic 9 lessons. So in the Basic 9, we are going to take a look at the first indicator, which says we should describe the conversion of decimal into binary data type for computer to recognize the meaning, process, and store. So under that, we are going to convert decimal, binary, and hexadecimal data from one format to another. We are also going to show the results of calculating two or more binary numbers using the mathematical notation or operators in the number base 2 rule. Yes, so without wasting much time, let's compute together. All right. So we look at the conversion of decimal into binary data. A digital system. When we say a digital system, we can understand it as a positional number system, only where there are a few symbols called what? Digits. And these symbols represent different values depending on the position they occupy in the number. So no, in the digital system, positions matters because the position of a number determines what it holds and what it stands for. So a value of each digit in a number can be determined using the digits, the position of the digit in the number, and the base of the number system. So we are going to take a look at three number systems. The first one, we look at decimal systems, which is normally called the base 10. So what at all is the decimal system? When we say the decimal system, it's mostly used in our daily lives. It's a positional number system with a base of 10, meaning it uses 10 digits, starting from 0 all the way to 9, making up what? The 10 digits. Great. So the digits being used, let's look at some of the characteristics of the decimal. The digits that are used is from 0 to 9, and then it depends mostly on positional value. What do you mean by that? Each position in a decimal number has a value that is a power of 10. For example, in the number 345, when we look at this number 345, the 3 is in the hundredths place, right? That is 10 exponent 2. Then the 4 is in the tens place, which is what? 10 exponent 1. And then 5 is in the ones place, which was 10 exponent 0. And we know that any number exponent 0 is 1. So the position here has put the 5 in the ones, 4 in the tens, and then 3 in the hundreds. That is why we pronounce this word 345. So example, 345 in decimal is calculated as 3 times 10 exponent 2 plus 4 times 10 exponent 1 plus 5 times 10 exponent 0. Remember, it starts from 0 all the way to 9. So when we are arranging the numbers, we start from the least one on the right, is 0, we go to 1, we go to 2. So after doing this, you realize that we will get, if we use the paired mass that we discussed in the previous lecture, we look at bracket first. So we'll calculate what is in the bracket first, then we'll go and look at the exponents, right? So when we do that, we get 300 plus 400 plus 5, which give us 345. Great. So let's look at the other system, which is the binary system, which is normally in base 2. So the binary system is the fundamental number system in computing. So this is where it gets a little bit complicated. So let's pay attention here. From the decimal system, we look at the base 2. The base 2, which is the binary, is what is normally used in computing. In the base 2 system, which means we only use 2 digits, which is what? 0 and 1. Each binary digit is known as a bit. So there's 0 bit and 1 bit. That's it. So characteristics. The digits that are used are only 0 and 1. Positional value. Each position is a binary number, has a value that is a power of what? 2. For example, in the binary number 1011 base 2, the position from the right to the left. Remember, in mathematics, our positioning starts from the right. Great. So from the position from the right to the left, 2 exponent 0, 2 exponent 1, 2 exponent 2, 2 exponent 3, respectively. What do we mean by that? When we arrange the 1, 0, 1, 1 in order, as we explained earlier, we have to start from 0, right? So 0, 2 exponent 0, 2 exponent 1, 2 exponent 2, then 2 exponent 3, as we did in the previous decimal system. So we multiply the 1 by the 2 exponent 3. This is in base 2, so we are multiplying by 2. That's why we have 2 here. And as I said, the positioning starts from the right. So we start from 0. That is why this side we have 2 exponent 0, 2 exponent 1, 2 exponent 2, then 2 exponent 3. So when we solve the ones in the bracket, we get 8 plus 0 plus 2 plus 1, which is what? 11 in decimal. So the number 11 in decimal can be converted into base 2 as 1011. And this is how the computer understands the number 11. You might think, oh, maybe there's 11 in this number, so what are we saying? No, actually the computer doesn't understand the number 11. It only understands zeros and 1. So you might see this as 1011 and say 11 is here, but this is actually in the bit system that we are referring to, which is normally what? 0 and 1. Or in the logical hardware, we say on and off. So 0 is off and 1 is on. So anytime you see the bits 1, 0, 1, 1, so for the computer to output the number 11, it will output 1, it will turn on 1, turn off 0, turn off 1, turn on 1 again to give you the number 11. So that's how the bit system works in computing for the binary system. Okay, so we take a look at the hexadecimal system. What do we mean by that? The hexadecimal system, or simply hex system, is a base 16 number system. It is often used in computing as a more human-readable representation of binary numbers. Because if you look at the way just 11 was represented with a binary of 1011, imagine the number maybe 97. How it will be represented in binary? Yeah, you can imagine how long it is. So the hex system was also introduced to make it more easy for humans to read the representation of binary. So hexadecimal is more compact and easier to interpret than the binary. Yes. So what are some of the characteristics? The digits used are 0 to 9. Remember, it's 16. When we had the decimal, we had 0 to 9, which gave us the what? 10 digits. So here we need 16 digits. So basically, you have to start from 0. So we start from 0 to 9. Since we don't have 10, 11 in that order, we represent the rest of the representation to get up the 16 with letters. So when we have 10, we represent it with A. When we have 11, we represent it with B. 12 is represented with C. 13 is represented with D, 14 is represented with E, then 15 is represented with F. Yes, so that is how the hexadecimal number system works. So positional value. Each position, as explained earlier in the hexadecimal number, has a value that is a power of 16. For example, in the hexadecimal number 2F3, the positions from right to left represent what? 16 exponent 0, 16 exponent 1, and 16 exponent 2. Right? So 2F3 can be an example of a hexadecimal. Remember, it's a combination of letters from A to F and then 0 to 9. So F is part 2 and 3 or 4 within the range. So we are correct here. So 2 times 16 exponent 2, F times 16 exponent 1, 3 times 6 exponent 0. Here too, we start from the right side. So the 16, as we are doing base 16, the first one takes 0, the second one takes 1, the third one takes 2. So when we do that, we get 2 times 256 plus 15 times 16 plus 3 times 1. And when we solve the bracket, we get 512 plus 240 plus 3, and then we get 755 in decimal. So 2F3, as represented here, simple like this, is rather 755 in decimals. Can you see the beauty of computing here? Representing the number 755 in just a hexadecimal number like this, which makes it easier for the computer to read. Remember, these conversions are not for you, the humans. It's for rather the computer to be able to use. Great. So what are some of their uses? So their uses in computing for the decimal system is not directly used in computing, right? Because as computers operate in zeros and ones, which is the binary, but it is mostly intuitive system for humans. Therefore, it is often used in higher level programming. So when we are programming, remember the time we were programming, we were dealing a lot with the the decimal system, which we were using the number 24 and the rest. So user interface and when outputting data for human interpretation. Great. What about the binary system? It is normally used for memory storage. Remember, anything you store in your computer is not stored in letters. It is stored in numbers, and it's not stored in the decimal numbers. It's stored in what? Binary. So in computers, all our data are stored as binary, zeros and ones. Even the picture that, even the PowerPoint document I'm using here, it has been stored in zeros and ones on the hard disks. Isn't that amazing? Yes, that is how the binary system is helping us in the computing world. So remember I explained earlier that the logic in the hardware, the logic gates in the hardware operates with on and off, which is the zeros and ones. So the computer processes uses binary for operation involving logic gates, which is on and off, 0 and 1, on and off, which perform functions like AND, OR, and NOT. Great. Then data transmission in computing over networks, storage devices, etc. is also often in binary form. That's the beauty. What about hexadecimal systems? How do we use them? It is commonly used to represent memory addresses in computing. This is because it's more concise than binary and aligns neatly with byte boundaries. Since one hexadecimal digit represents 4 binary digits or enable, so 4 binary digits is called enable, right? 8 is a byte. So instead of representing that long chain of bytes or zeros and ones, you can use just one hexadecimal to represent it, and that is the beauty of it. Then color representation. In web design and graphic design, hexadecimal is used for representing colors. Yes, let's quickly look at how hexadecimal helps in representing colors. So let's say I take this header, right? I want to change the color. So I go to the font size, I'll go to more colors, then I'll go to custom, right? So you see here hex. Remember when we were discussing it, we said the short form can be hex. You see the hex number here. They've given a number here, a representation FF0000. Great. So let's do that and see what color we'll get. F, so two F's, then four zeros. So when we press, so remember the current color is yellow, right? So let's press OK. So you see it has changed, meaning that FF0000 is red. So let's change that color to and see. So that's how colors are represented in hexadecimal. So let's do 4Fs rather instead of uh, 4 zeros. So let's do FF again. Let's press OK. Then changes back to our yellow. So to get yellow, you do FF00. To get red, FF0000. So I want you to practice what will happen if you do all Fs or all zeros. Great. So that is how we use hexadecimals to represent colors. Great. Then we look at how to convert the various systems. This is where the lesson gets interesting. So we are going to convert decimal into binary. We'll also convert binary to decimal. Then we'll convert decimal to hexadecimal. Then we'll convert hexadecimal back to decimal. Then we'll convert binary to hexadecimal. Then we'll convert hexadecimal to what? Binary. Isn't it cool? Yes. So let's get straight into our lessons. So we are going to start with decimal to binary and then convert back binary to decimal. Okay, so let's look at it using Word document. We are going to use the table, a simple table to show our demonstration. Before that, let's look at the numbers we want. So let's do 24 in base 10. Then we'll do maybe 53 in base 10. Great. So we will convert these two into binary, then we'll convert them back into decimal. So we'll have our table, then the first column will have operation, the second column will have results, then the third column will have remainder. Great. So 24, we divide 24 by 2. What is our result? Yes, 12. Is there any remainder? No, so we put 0. Then we take 12, we divide by 2. 12 divided by 2, we get 6. Is there any remainder? No, so we get 0. Then 6, we divide 6 by 2. Remember, we are converting to binary, so that's why we are using 2. So 6 divided by 2, we get 3. Is there any remainder? No, so we continue. 3 divided by what? 2. What do we get? We get 1. Is there any remainder? Yes, 1. So the reason why we have this 112 here is 2, 3 divided by 2, you get 1. 6 divided by 2, you get 3. So we have our 1, 1, 0, 0, 0. Great. So we will, since 2 can no longer divide the number 1, 1 can no longer divide it. So this is going to be our answer, right? So let me shade this table. So this is going to be our answer. Great. This including this, yes. So 24 base 10, let me copy this. 24 base 10 will give us what? 1, 1, 0, 0, 0 base what? 2. Great. So let's check if our answer is correct. Let's convert this back into base 10. Now, what we are going to do is we are going to follow the same procedure in the beginning of the lessons. So 1 times 2 plus 1 times 2 plus 0 times 2 plus 0 times 2, then the last one plus, plus 0, 0 times 2. Great. Remember, we have to give them exponents starting from 0 up to the last 2. So this number here 2, we take the first 0 here, 0. Then we move on to the next one, 1, 2, 3, 4. Great. So now we are going to solve this as we are supposed to. So 2 exponent 4, we will get 2 times 2, which is 4. When we multiply 4 by another 2, so we have 2 times 2 times 2 times 2. So 2 times 2, which is 4, multiplied by 2 again, which is 8, then multiply by 2 again, which is 16. So we have 1 times 16 plus 1 times 8 plus 0 times 4 plus then 0. Any number raised to the power 0 is what? 1. Yes, so 0 times 1. Then we solve this here. So 1 times 16 we get 16 plus 1 times 8 we get 8 plus 0 times 4 we get 0 plus 0 times 1 we get 0. So what do we have here? We have 24, which is in the base 10. Great. So this is how we convert base 10, which is decimal, into binary. Great. Then we convert the binary, which is here again, back into the base 10. So if you do your conversion and you're not getting the right answer, your problem can normally come from here, especially when it comes to the writing of the binary numbers. Great. So for the sake of time, I'll leave this as an exercise for you. you can use this to do your conversion decimal to binary, then binary to decimal. So quickly look at the next one, which is decimal to hexadecimal. Great. So decimal to hexadecimal, let's convert the number 756 to hexadecimal. So 756. So we are treating right now, we are doing decimal to hexadecimal. So this was decimal to binary, and then this was binary to decimal. Now we are doing decimal to hexadecimal. Great. So we are going to take the numbers 756 in decimal, which is in base 10, to hexadecimal. So what do? We use the same procedure of taking the remainder and all those stuff, right? Okay, so let's get our table ready. So I'll just copy this table, paste it, then I can empty this table here. Great. So we pick our 756, we divide by 16. What is the result we get? 47. 47 remainder what? 4. So we take the 47 to 47 divided by 16. Then what do we get? 2. 2 remainder what? 15. Remember, we don't write 15. So we are going to do what? F. Great. So what again? 2 divided by 60. We don't have 2. So we are going to just end our this one here. So let's remove this table from here. Let's delete this table. Great. So now we have this here. 2, since 16 can no longer divide this number, so we are left with what? 2, 15, 4. And remember, we don't have 15, so we are left with what? F. So we are going to get 2F4, which is base what? 16. 16. Yes. So the number 756, which is in decimal, we convert it to hexadecimal, we get what? 2F4, which is in base 16. Great. So now let's convert this hexadecimal. Let's convert this hexadecimal to decimal. Great. So we take this as the question that we are going to convert, and we do the normal system that we have here, right? So we take 2 times 16 plus f times 16 plus 4 times 16. Yes. So as usual, we start from here, 0, 1, 2. So we get 2 times 16 exponent 2 times 16, we get 256. 256 plus, so here we can now convert our f into number, which is what, 15. So we get 15 times 16 plus or times 1. Great, because any number exponent 0 is 1. Okay, so let's add these results. So 2 times 256, we get 512. Then we add 15 times 16, we get 240. Then we add 4 times 1, which is what, 4. So we get 756 as we had here, which is supposed to be in base 10. Great. So here we've been able to change decimal to hexadecimal. Then we've been able to change back the hexadecimal to decimal. Great. So in our next lesson, we are going to look at binary to hexadecimal, then hexadecimal to binary. So to achieve this, let's use binary to hexadecimal. Let's start. Binary to hexadecimal. Interesting when we get to this side. So what we have to do here is we have to group the binary digits into sets of 4, right? Starting from the right. So we convert each group to its hexadecimal equivalent. So let's take, let's say the 11011010, right? Base 2, and then let's convert into hexadecimal. So what we have to do here is to group them into groups of 4. So we take the first two here, starting from the right. So we have 1010, right, which is at this side. Then we take the other one, which is 1101. So this first one, let me highlight it, give it more, you see the difference of what we are talking about. Yes, I will use. So this is the first group, this is the second group. So the first group is the 1101, then the second group is the 1010. So what do we do here? Then from here we convert this into hexa. So when you are able to group them this way, this is where it gets interesting. You have to convert this into decimals. Yes, you have to convert this into decimals before you can get it back into hexadecimal. So converting 1101, we convert it into decimal. So let's quickly go there. So 1 times 2, right? We are converting it into decimal. Then 1 times 2 again, plus 0 times 2 plus 1 times 2. Great, that is for the first one. So as usual, we put our 0 here, put our 1 here, put our 2 here, we put our 3 here. Great. So we are just going to quickly jump into it because we've already gone through the steps. So 2 times 2 times 2 we get what? 8. So we have our 8 plus 4 plus 0 plus 1. So this will give us an answer of 13. Great. And remember, let's go to our table, our hex table. When we have 13, 13 is what? D. 13 is D. So since we've been able to get 13 as a decimal, then we convert the 13 into hexadecimal. So we get D, which is in what? 16. And the 13 is in 10. But we are not done. This is only the first part. So we'll do the same for this part. Right. So let me just copy this to make it easier. So here we just change the 1. Here becomes 0. Here becomes 1. Then here becomes 0. So 1 0 1 0. Great. So when we do it, here too we get 8 plus 0 plus 2 plus 0. Yes, so 8 plus 0 plus 2 plus 0, and here we get 10. And if you look at our hexadecimal, A is 10. So we get 10, which is in base 10. But when we convert it into hexadecimal, we get A, which is in base 16. So after this, finally, we arrive at what? Remember, the number was together, they were not separate. 1101, 1010, which is in base 2. Then we convert it, then we get what? So the first part we had D, the second part we had A. So we combine them, we get what? DA, which is in base 16. So that is how you quickly convert any binary into a hexadecimal. You just have to make sure that you're able to group them into groups of 4, even if it is let's say 6, right? 6 numbers. So let me just give you an example. If maybe it is 1 1 0 1 1, right? So here is 5 numbers in base 2, right? We have 5 numbers here in base 2. How do we group this? Yes, so you take the last 4, so this becomes the first 4, right? So 1 0 1 1, this is the first set. Then you have this number, this one, the last one here, as the only one available. Don't worry, just write that one and replace the others with 0. So when you get a number like this and you're supposed to convert it into hexadecimal, don't worry, just take the last 4, 1 1 0 1, which is this one. Then you take the last set also starting from the right, which is 1, which is only this one. Then the rest will be what? 0. Yes. So that is how you do it. And it's pretty much simple. You just convert it into decimals. Then you pick the first one as we did here, pick the second one, and you put them together. Great. If you have any questions, leave it in the comment section and I'll be glad to reply you. We look at the last part, which is what? Converting hexadecimal to binary. Converting hexadecimal to binary. So that one, how do we do that? A very simple procedure. You convert each hexadecimal digit to its 4-bit binary equivalent. As simple as that. It's even more simpler than the first one. So if you have maybe the 3F, right, which is maybe in base 16, we are supposed to convert this into binary, right? What do? Is we take the 3 and we find this equivalent in binary. So let's quickly convert 3 into binary using this uh, formula here. Let's quickly go through that. Great. So we get 3 divided by 2, we get 1, and we get what? 1. So we don't have anything left, right? We don't have anything left. So this is going to be our answer. So we are going to delete this part of the table. We don't need it. So to demonstrate, this is the only part we need, which is the 1, 1. So here we get what? 1, 1. Then we do the same for the other. Do the same for the other number, which is what? F. And we know F is what? Yes, you are right. F is 15. So take 15, we divide by 2. By 15 by 2, we get what? 7, remainder 1. Then we take 7, we divide by 2, we get what? 3, remainder 1. Then we take 3, we divide by 2, we get 1, we remainder what? 1. Beautiful. So here, this part we don't need, this one is not part. Great. No color. Then here we get what? 1, 1, 1, 1. Great. So remember, it's always in 4 bits. So here we've gotten our 4 bits, which is okay. But here we didn't have our 4 bits because it is only 1, 1 we had when we converted 3 into binary. And remember here, we learned that whenever we are converting binary to hexadecimal and we have only one number here, we add zeros to do the conversion. Yes, we do the same thing here. We have to add zeros to it. So here, what we'll do is we'll do 0, 0, 1, 1, and the zeros are coming from the zeros we added here. Then we add the 1, 1, 1, 1, which is this set. So this set is the set for this side, and this set is the set for this side. Then we put it in binary. That is how we convert any hexadecimal into binary. A very simple procedure and easy to go about. So we have been able to cover that part of their lesson, which is what? Conversion between systems. Great. The last part of the lesson, which we are supposed to discuss, is show the result for calculating 2 or more binary numbers using what? Mathematical notations. Great. So let's quickly go on into that. But to start with that lesson, I'll first want us to do something quickly. We have to convert 3 and 2 into binary. And we've already done 3 here. 3 base 10, right? 3 base 10 into binary is what? 1, 1. Great. What about 2? So 2 base 10 into binary, right? 2 base 10 into binary is 0, 1. Sorry, 2 base 10 into binary is 1, 0. Great. 1, 0, because when we divide 2 by 2, the result is 1, yes, but the remainder is what? 0. So with this, let's quickly solve 1 or 2 questions under multiplication of binaries together. So let's add 1, 0, 1, 1, and let's maybe add 1, 1, 1, 1. Great. These four numbers. Let's give them space to make the calculation easier. It's addition. So great. So we space them out neatly. Then we are going to give the answer. So here you understand why we did this first. Great. So 1 plus 1, we are calculating binaries. So we don't need any number aside zeros and 1. So 1 plus 1 will give us 2, but we can write 2. So what do we do? What we'll do is that we will look at this table we have here. 2 is represented with what? Zeros and 1. And since position is very important in the number system, remember when we are adding, we take the 1 at the right and carry the 1 on top. So here we will write 0 and carry the number 1 on top here, on top of this 1. Yes. So we have 0 here and that 1 here because we had what? 1 plus 1 to be 2. So we've not lost any of them. Great. Now we add this 1 to this 1, which gives us what? 2. Now we add this 1 and this 1 to this 1, which gives us what? 3. So what is the answer for 3 from our table? It's 1, 1. So we pick the first one on that side, 1. Pick the first one from the other side, which is 1. Then we carry the other one on top. Great. So we carry the other one on top. So now we still have our 1 plus 0, which is still 1. Then 1 plus 1, we get what? 2. And 2 here is what? 1, 0. So 1, 0, we write the what? Yes, we write the 0. Yes, we write the 0. Then we put the 1 over here. Great. So now we have 1 plus 1, which is 2, plus another 1, which is 3. So this 3 here is represented in binary with what? 1, 1. So we write the first 1 and we carry the other one into another column. Great. So let's space this out to give room for that. Yes. So we space it out to give room for that. So now we are left with this 1 and there's nothing here. So we have 1, 0, 0. So 1 plus 0 is still 1. So we put the last one here. Great. So that is how we add two numbers in binary to get a result. So let's quickly go over again. We have 1 plus 1, which gave us 2, right? So 2 in binary is 1, 0 because we are calculating binary. So what did we do? So we picked this 0 and then represented the 1 as a carry on top here. So this is the first one that we have here. Great. Then what did we do again? This is the first one that we have here. Great. What did we do again? We added this 1 to this 1 to this 1, which gave us what? 3. And 3 in binary, we have 1 and 1, which gave us what? 2. Sorry, which gave us 1 and 1. So we represented the first one on this side here and the second one on this side here as a carry. So now still have the 1 here, 0 and 1. That gives us what? 2. So 1 plus 0 plus 1, which gives us what? 2. So 2, we have the 0 here, represent the 0 here. We have the 1 here, represent the 1 here. So here too, we take 1 plus 1 plus 1. It gives us 3. So here we take the first 1 here, represent it here. Take the second one here, represent it here. Then we have 1 plus 0 plus 0, which gives us what? 1. Great. So this is how we add two binary numbers to get another binary. So adding 1011 to 1111 will give us what? 11010. Right. So we've covered a lot in this lesson. We've been able to convert all these numbers into their respective bases. Right. So this is where we will end the first indicator lessons. Then we'll continue with the second indicator in another lesson, which is more interesting because we are going to do scratch programming. Great. See you in our next lesson. Bye bye.